I hope that's doing what it is supposed to.
Yep, that looks good.
Okay.
All right, so welcome everybody to the latest installment of the GBO NRAO Science Lunch meeting and talk. Today we'll be hearing from Victoria Butler, who is a PhD candidate with the Astrophysical Sciences and Technologies program at the Rochester Institute of Technology, where she's working with Professor Mike Zemkov. Today, we'll be hearing her talk about her work in measuring the SC corrections with massive clusters. So when you're ready, take it away, Victoria.
Thanks, Jesse. Hi, everybody. It's interesting to give a virtual talk. I haven't done very many of these in Zoom in COVID times, so this will be fun. Jesse said most of the important stuff about me. I'm going into my 5th year of my PhD, and I probably have about 1 more left to go. So reaching the end of the line there. I've been told this is slightly more informal. So with that in mind, I'd like to invite everybody to interrupt me as much as possible during the talk in the middle if you'd like. There's no need to save everything until the end. It also will keep me from feeling like I'm just talking to my empty bedroom since I can't see your lovely faces. So I guess I'll get right in it, and thank you guys for inviting me. I really appreciate it. So the first thing I'm going to mention is all of the little pieces that you need to know in order to understand why this research topic is important. And so, as Jesse said, I'm going to be measuring SC corrections in massive clusters, and more specifically, I'm going to be using that correction to estimate the temperature of the intracluster medium, and I'll explain a little bit what that means in a moment. So my talk's going to be broken up into a few sections, which I'll explain in the context. I have to tell you what makes clusters special enough to study in the first place, what the SC effect is and how we measure these corrections, and then we'll discuss the specifics of how I study this effect and what kind of impact we can expect from this work to our field. So I want to start by taking a huge step back and going back to the beginning. Clusters are a huge collection of individual galaxies that are all held together in a dark matter potential well. And the void between these galaxies is filled with the intercluster medium, which is a superheated plasma that's between 10 to 100 million degrees Kelvin, and it emits heavily in the X-ray. So by studying clusters at different redshifts, I'm effectively studying the evolution of large-scale structure, which is what this illustrious simulation cutout is capturing. So the most massive clusters are believed to exist at the intersection of dark matter filaments called nodes. So in this image, it's the purple are the filaments, and then the nodes are these bright globule structures connected between them. And this indicates that there's some sort of coevolution between the dark matter aggregation and the cluster mass. So a large fraction of the baryonic mass connecting these clusters and within the clusters themselves is not currently detectable, either because it's too diffuse or too cool to study in the X-ray, meaning there's plenty of exciting room for further study here. So please forgive my little cartoon drawing. Turns out that when your computer has lag, drawing letters is hard. So there's other processes occurring within the clusters themselves that are not well understood, but which also affect the evolution of the cluster environment. Some of these processes can change the temperature of the intercluster medium in unpredictable ways. Our most basic model for clusters is that they're a spherical dark matter halo that gravitationally pulls the gas in the ICM towards the center. And this gravitational heating is considered the primary heating mechanism for the plasma. And that temperature can be determined by the virial theorem, which I've given on the left. So this model incorporates the total mass of everything in the cluster, which is MV, all the mass within what we're calling the virial radius, which includes the member galaxies, dark matter, and the intercluster medium mass. And it also includes, so the mass of the ICM is this mu MP, the ionization of the ICM, and then the virial radius on the bottom. So unfortunately, reality doesn't often match this model. So we're not always going to have a bound virialized system. It's not always going to be in hydrostatic equilibrium, right? And maintaining the balance between gravitational heating and radiative cooling through free emission doesn't always work in every system. So what I'm showing on the right is a system which could be very, very massive. And in this instance, there's a temperature gradient across the ICM, where the central region is the densest and the hottest, and it therefore also radiates the most efficiently. So this causes, in contrast, the central region to be cooler and hotter gas from outer layers to collapse inward as the pressure in the central region drops. So with this kind of mass deposition, you should see clusters with cool cores that have significantly high star formation rates and relatively low central temperatures. Instead, in many of these systems, we see relatively normal star formation rates and higher than average central temperatures. So perhaps there has to be some other heating mechanism to explain why we see what we do. I'm going to show you a little video. One of the proposed ways is through mechanical feedback from an active galactic nuclei, which the Perseus cluster is a really great example of, and I'll show you this video. So this shows a zoom out of a Hubble image of the cluster member galaxy NGC 1275, which is superimposed on a ground-based image, and then it zooms out to show the full field of view for the upcoming Roman Wide Field instrument. And this is just to illustrate sort of what a cluster would look like in the optical. However, this optical image is hiding some of the exciting ICM physics that's ongoing thanks to this AGN, which is inside of the brightest central galaxy in the cluster. So the bottom left photo shows an X-ray image taken by Chandra, which reveals several X-ray cavities from what are believed to be past jet events from the black hole, and which have potentially heated the ICM. So if you look in this purple image, you can see to the north and south are these X-ray cavities that we're talking about, which are essentially the jets blowing out the ICM as they're expanding and then leaving these cavities in their wake. So the upper figure is a hydrodynamical simulation of a Perseus-like cluster in a snapshot taken about 300 megayears after an AGN released a jet into the ICM. So this simulation found that the shocks from the jets caused anisotropic heating to the ICM perpendicular to the jet axis, making it a viable source for increasing the ICM temperature. So there's a lot of people that are doing really great work trying to prove that maybe this AGN feedback is the heating mechanism we've been missing in our models. I'm going to talk to you about a different observable that can also help study these thermodynamic processes in a slightly different way. And this is the Sunyaev-Zoldovich effect, which some of you may have heard of before. It's getting a little bit more popular in the talk circuit. It was theorized originally back in the 1970s by the two scientists that it's named after. And the SC effect is it's a distortion in the cosmic microwave background spectrum. So photons from the CMB, which I've drawn over onto the left here, coming from about a redshift of 1100 or so, act like a scattering background where they gain or lose energy to the electrons in the cluster. And then they're re-emitted for our detectors to measure at Earth. So now what I'm going to show you is the spectrums of what those two look like, the ins and outs. So this inverse Compton scattering modifies the original CMB spectrum, what I'm showing on the left here. And I have it in units of frequency in gigahertz all the way up to 1,000 And then the intensity on the y-axis, I've put in megajansky per steradian. Since you're all radio people, I really hope that's okay. This is the units that I work with day to day, so that's why it's that way. On the right-hand side, what I'm showing is the thermal SC effect from the scattering due to a thermal population of electrons, which steals photons from lower frequencies and pushes them to higher energies. So the spectrum of the thermal effect is shown here for 3 different gas pressures presented as Compton Y values. Sometimes in extremely massive clusters, there's a population of electrons whose energies are relativistic. So this presents as a correction to the thermal SC effect that we just showed in the previous slide, and it results in a slight shift to higher frequencies. So I've plotted here the thermal effect in red with the RSC corrections due to 3 different temperatures in the purple. There's also a correction due to the SC effect from the peculiar motion of the cluster relative to our line of sight. So the cluster moving in front of our field of view. This effect is a really tiny, tiny amplitude compared to thermal. So it's very, very hard to measure. And it's been enhanced here by 50 times just so you could see it on the plot. But the sign of the amplitude, you might be wondering why it's upside down. It will flip depending on which direction it's moving, either towards or away from the observer. My project involves measuring just this relativistic SC effect in the submillimeter in multiple galaxy clusters. So I'm interested in probing the deviation of the purple line from the red line. The SC effect is a really natural complement to existing X-ray cluster studies, and that's for 3 very important reasons. One is that X-ray instruments have a limited temperature sensitivity. Usually it's between 10 to 15 keV, but I know some of the upcoming and existing like Xray telescopes will push that further. Some of the most massive clusters, though, they have temperatures up to 20 keV or higher, making that a little insufficient to probe the actual temperature of the ICM. For the SC effect, an increase in temperature is actually an increase in our signal, making it easier to measure. So if you see on this plot again, 15 keV is this line here, which is much, much further away from our canonical thermal spectrum. So that's why. Another couple of shortcomings can be seen in the equation for the X-ray brightness, which I've included right here. And the problem with this is that it depends on not only the redshift to the 4th power, which is hugely detrimental, it's also dependent on the integrated electron density squared, this term back here. That means that the X-ray instruments are hugely sensitive to cosmological dimming, and they have a very hard time observing more diffuse gas like what exists in cluster outskirts. In fact, 50% of the baryonic matter in the universe is believed to exist in this warm, hot intergalactic medium, but we can't currently observe it in their X-ray because the densities are just too low. So what I've concluded below that is an equation describing the SC spectrum right here. So this is actually, we call it delta I because it's the change in the CMB intensity, but we just call it delta I SC. And it has the functional form presented by G of X here. I naught is just this factor that has to do with the temperature of the photons that we're receiving. In this case, they're from the CMB, so it's a constant factor. And then Compton Y, again, is like an integrated pressure term for the gas that's in the ICM. So that's what those 3 things are for. So what you can see here is that there's no strict dependence on the redshift for the SC effect. And the Compton Y value is only dependent on the integrated linear electron density, this term here. So this means that it can effectively study more diffuse gas at any cluster redshift compared to X-ray data. So the RSC effect that I'm measuring is actually this tiny little delta term you see here at the end, right? So what I'm showing here is the formal thermal effect equation. And then the correction due to this relativistic populations is just this delta x of t. And it's only a function of the observing frequency and the temperature. And that's what makes this super valuable for measuring the temperature of the ICM. So I don't know if any of you have heard about the thermal SC research that's come out of the Planck satellite, but the thing that makes measuring temperatures tricky with the thermal effect, despite the name, is that it's heavily dependent on this Compton Y factor, right? So when you see a change in the SC spectrum, you're not sure if it's due to just the temperature or if it's also due to the properties of the gas changing on you at the same time. So what makes RSC so unique is that it's not subject to the density. You have to have a good initial guess of what that gas density is, but what you're actually probing is exclusively the temperature. So that's why this is so cool. So I'm starting my work on just one cluster. And the one that I've decided to start with is RxJ 1347.5-1145. And it's been really heavily studied by almost every wavelength you could think of. Some of these are optical and X-ray. The image on the right is actually data from Chandra, shown in purple. And overlaid on that is HST and SDSS optical data. So you can clearly see the central BCG here. That's this guy right there. But what's more interesting and harder to see is the suspected ongoing merger. So what I'm going to talk about for most of the rest of this talk is the pipeline that I've developed to take the submillimeter data for this cluster and turn it into an estimate of the SC amplitude and thereby determining the temperature of the ICM. So before I get started, does anybody have any questions about the background and sort of what we're trying to do? Okay, sounds good. Well, let's go ahead then. So I'm using archival data from the Xray Telescope, which looks wildly different than the optical or X-ray data I've previously shown you. The Herschel Space Telescope was launched back in 2009, and it reached the end of its mission in 2013. The Spire instrument on board had 3 bands, shown here ranging from 250 to 500 microns. If you want to talk about that in frequency space, it's somewhere between 500 and 1200 gigahertz. And the funny thing about the image is, the false color image on the right was made by combining these 3 bands into a composite. And the funny thing about it is that you can't see any cluster member galaxies besides the central BCG again that we mentioned before. The point sources in the image are actually mostly fields of background and foreground galaxies, some of which have become lensed. And you can't visually see the SC effect by eye, right? Like most people would expect, if you're talking about an observable, obviously you must be able to see it in a map of the cluster. You actually can't see it by eye because there's so much else going on. And this is one of the real struggles of measuring the SC effect in the submillimeter, is that there's many, many different sources of contamination, and the relative signal strength of the SC effect by comparison is very small. So our job really is figuring out how do we model all of the other components in this image so that we can just isolate the SC amplitude that we're interested in. So forgive my continued cartoon developing. I think I'm a great artist, apparently. But what I've made here is a cartoon representing what I think a submillimeter cluster image contains. I've left the image of RxJ in the corner for a reference so you can see what I'm talking about while we break this down. So since all the clusters exist at redshifts lower than the CMB, it's naturally a background. And it's the source of the photons that we're interested in. So I've included that up here. There's also a field of background galaxies below the spire detection limit, and these become lensed, excuse me, due to the mass of the cluster. And this contributes to some of the confusion noise in the image. So the SC effect is also spatially coincident with the center of the cluster and this lensing deficit, which further complicates the measurement. And what I mean by lensing deficit, which I'll show you an example of a little bit later, is that when you lens a system, you tend to get this hole in the middle, right? And the SC is spatially coincident with this hole. And the reason it complicates the measurement is if you don't account for the fact that there's lensing there, you might overestimate the amplitude of your SC effect unwittingly. So we also have foreground galaxies in our image that appear as point sources again. And finally, we also have gas within the Milky Way, which we're going to call cirrus. So each of these components must be modeled and or subtracted to isolate just the RSC signal. And also keep in mind, this is just a toy model. There are many, many things that could be in this universe that I'm not accounting for. And so these are just the basics that we can cover. So the modeling and subtraction of point sources in the image is handled by a pipeline that I developed along with 2 undergraduate students here at RIT, Ben Vaughn and Dale Mercado. Dale's actually since become a master's student in our department, and he's doing his own research project now. So sadly, we also haven't come up with a cool acronym for this pipeline yet. And I know that's kind of standard when you start writing your first paper, you have to give your code a cool title. So if you guys have any ideas, let me know. I'm still trying to figure one out. I'm showing here what a typical workflow looks like for our real and also simulated spire image. And I'll tell you in a moment why we need a simulated image. So we have 3 distinct parts. We have the real or simulated data sets that we're bringing in. And I've shown an example of RxJ here. Excuse me. The point source detection software is the thing that happens in the middle, which does each of these 3. It will model the sources in the image, subtract them out, and then we will remove any kind of correlated residuals in the image that happen to be there. So finally, what we do is we say, okay, well, whatever's left in the image better be the SC effect. And then we measure that amplitude and then fit a spectrum to it, which I'll explain a little bit more in a moment. So, sorry about that. Typically what will happen is we'll decide whether or not we're working on real or simulated data. This will all get saved into sort of a Python dictionary that we modify as we go through our pipeline. And it can include things that are not just this image, but also a noise model for the Spire instrument, an exposure map, which tells us, hey, here's how Spire went through and observed the field that it's looking at. That's kind of why you see this sort of hashed imaging, because it's just where the telescope turned around and went back. So you can actually see that it kind of did its scan sort of diagonally through the image and then went back and forth the other direction again. So it just tells us whether or not, you know, we're averaging photons over a certain number of exposures. So I'm going to break this down even further because this is kind of a lot of information. But the first thing I'm going to describe to you is our need for having simulated data, and also to motivate our discussion about the point source modeling software we're using, which is called PCAT. I know a lot of people in the field are very used to seeing like Starfinder or XID Plus talked about. We originally started using that in our analysis, but we ran into a lot of roadblocks with it. And my advisor just happened to be working with another student at Caltech named Richard Fetter, who was developing this point source removal software. So lucky happenstance for us. So we create our simulated maps for a given cluster in order to test the systematics that are introduced by different components in the image, whether it's coming from instrument noise or the lensing effect or some other thing that we haven't accounted for. So if we change any one of these templates, we can test and see how the measured SC amplitude changes with it. So starting from the left, we have a realization of the noise from the Spire instrument, and this is taken from the real data set. Then on the right, we have a mask to isolate just the data that we're interested in. So anything that's in this white region is something I'm telling it, you can pay attention to that data, don't worry about the rest of it. And then on the bottom left, what we have is a field of point sources that we've convolved with the Spire PSF and then lensed using some lensing code from a few other authors. And that's the GIF that I'm showing, the before and after the lensing effect. And so our final output map is the lensed version of this map with the noise added to it. So this is supposed to look entirely like the realistic Spire map. On the right, we also have a few other bits of information. So the first two on the top are the real Spire error and exposure maps. I talked a little bit about the exposure map. This has the number of scans over a particular pixel. And the exposure map, the error map is how we make our noise model. And it's the instrument noise. So the bottom left figure is actually one of the most important templates. Sorry about that. It's one of the most important templates that we have. And this is created using data from another SC instrument called Bullicam. And if you're interested in any of the research that has been done with that, you can look at Sayers et al. 2012. He's one of the collaborators in our group. And this instrument has done a lot of really great work looking at the kinetic SC effect, which I told you before is really difficult to measure. So what this gives us is we're telling our map, here's the shape and the extent and the position of where you should expect to see the SC effect in the image. But the amplitude has been normalized, so we can fit our own amplitude onto this template when we see fit. Mm-hmm. So the last image that I've shown here looks a little bit like a fuzzy blob. That's intentional. It's a dust map trying to represent the cirrus that the Spire image instrument would have seen directed towards the cluster. So it's the gas in the Milky Way between us and the cluster that it saw. Much to our chagrin, pretty early on, we realized that RxJ was one of the worst cases in our cluster sample for cirrus. It happened to be very significant, more than we were expecting. So we've actually had to devote a lot of time we weren't expecting into trying to model what this would look like and also try to remove it in a unique way from our data, which I'll talk about in a little minute. So we actually made this dust template from a Planck 2015 data release. Planck did an all sky map of optical depth values. And then we can use those values to extrapolate it into Spire wavelengths and make this map, depending on what pointing we're using. So we're using all of these pieces of information and passing it on to this point source removal and modeling software. And I know that seems kind of weird because I've only told you that all it does is it models the point sources and removes them from the image and creates this clean residual. But in order to do that, what you have to do is tell it, how much of the flux do I expect in the image to be from the point source? And how much of the flux do I expect to be from these other things? From the noise from the instrument, from the potential dust in the image, from the actual SC effect. So in order for it to actually subtract off the point sources and leave the SC effect alone, right? We don't want it to over subtract sources that are on top of our SC effect. We need to tell it what all of these other things are and how significant they are in the image. So hopefully that will make more sense in a second. So the software we're using, PCAT, performs crowded field probabilistic cataloging by creating a model of the image, and it assigns a prior estimate for each of the values of each component within each pixel of the map. So what I'm saying is, in this top left, or sorry, this top right figure, this is what PCAT saw when we gave it the real Spire map for this cluster. And it identified all of these point sources based on these red X's. And then it also was given a template of the SC effect, which you can see as this purple smudge right here. It has to decide in a given pixel how much component it's getting from each of the templates that we've given it, and then decide what to do with that information and what the posterior should look like, or the best fit model. So what I've included in the middle here is an example of Bayes' theorem, where in our case, we have a catalog ensemble and it has a prior that penalizes unrealistic models. And some of the things that we encode in this prior, for example, for the point sources, are what's their position, what's their flux, and what's the color we should expect across the 3 bands. So it actually does a multi-band fit. It doesn't just look at just one of the bands at a time, like the bluest band. It will look at all 3 based on that color prior. So the likelihood then compares our model image with our data. And whichever combination of priors fit the data best is considered our best fit catalog. So then it uses this catalog, which you could think of as all of these red hashed points, to identify and remove the point sources from the image, which is shown in this GIF here. And so the GIF is showing you basically multiple different models that were created, how many point sources were detected, how many samples it had to create in order to actually fit the data properly. So usually we have about 2,000 samples for each of the models that we're creating and averaging over. And then what you're seeing in the last panel is just what our catalog is subtracting from the image that we gave it. And you can see it's actually very smooth, and it looks like the instrument noise, which is perfect. That's what we were interested in. So afterwards, we can use whatever is in this residual, which is hopefully also the SC effect, and fit the Spire amplitude. So we're very lucky in that PCAT is also capable of fitting the value of the amplitude as one of its posteriors. And so I collect that as a piece of information at the output from this software. So just for context, also the field you're looking at in this bottom GIF is goods north, as it was observed by Spire at 250 microns. Okay, that was a lot of information, I'm sorry. But this is the juicy bit that I really like. So using this method, after we get these output amplitudes from PCAT in each of the 3 bands, that's what I'm showing here on this spectrum. These 3 data points were the output out the back end of PCAT, and the error bars were also from PCAT as well. It estimates the error on its posterior for us, which is amazing. So we take that amplitude and the uncertainties for each of the 3 bands, and we generate a best fit spectrum. So this is done using a fast SC numerical code called runscpack, which has honestly been a godsend. It's been amazing. It literally will calculate a spectrum in nanoseconds. It's fantastic. And the way we do that is we provide it a grid of possible gas densities and temperatures. So I'm going to show you kind of what that looks like. So in this particular example, we're looking at, we gave runscpack densities between 1.2 and 2.4. And these are times 10 to the minus 4. And then we gave scpack a temperature range from 0 to 14 keV. And we're basically forcing runscpack to just generate this entire grid worth of spectra for us. And then what we do is we perform a maximum likelihood analysis where you have a 68 and a 95% confidence contour shown in the heat map. Sorry, I saw some, I think some chats popped up, but it's not letting me click on the chat window. Jesse, is there something I should look at before I keep going?
I can just read it out to you real quick.
Okay.
So yeah, David Freyer commented, for priors, can you use deep, higher resolution data such as Herschel, PAX, or Spitzer MIPS 24? But since the point sources are dominated by SMGs, perhaps you are limited to using the longer wavelength Spire data.
Interesting. So it's funny that you mentioned SMG. You sort of stole my thunder a little bit because we're going to talk about how we used SMG in the Goods North field to test our dust removal software that we've been working on within PCAT. So it's actually an incredibly well-made point. It actually is the whole point of why we're doing what we're doing. We don't want to just use the higher wavelength bands because we get a better constraint on the point sources in the image from using the lower frequency, the bluer map in Spire. And in fact, the most important part of this project is trying to both measure that high amplitude point in the blue bands, and then also correctly modeling the far infrared thermal dust emission that's happening in the lower half. And so in fact, that's kind of what's happening here. Our first fit from PCAT had these points well above where they should have been sitting on the spectrum, despite the error bars, which that should always concern everybody. If you ever have a fit and your uncertainties don't sit on the line, you're kind of freaking out a little bit. But we think this was due to dust, and this is why we started investigating that. Sorry if that didn't really answer your comment at all, but hopefully the next couple of slides will show you what we've been doing to help still continue to use all three of the bands within Spire. But the MIPS 24 is also a good point. It's something that we tried using at one point, but we found the Planck dust maps actually were a little bit higher resolution and easier to use. Were there others, Jesse, that I should tackle? I saw another one pop up.
So Brian Mason commented, so the low frequency point is Planck.
Oh, I'm sorry. You're talking about this one down here. I should have made that more clear. This one's actually the Bolacam estimate of the SC amplitude. So while we also get the SC template from Bolacam, they did their own independent fit to the spectrum, but they did it only at 150 gigahertz. So it's just another constraint on the spectrum that we're making. I'm sorry, I should have made that clear. Thank you for pointing that out. Okay. Great. Is there anything else that I should look at, Jesse?
No, that was all the comments. And I'm sure you're coming to a close in a little bit, but everyone is also welcome to just unmute themselves and chat if they wanted.
Yeah, definitely. I know this is going a little bit long. Thank you for sticking around. I'm actually just about to hit my future work slide, which we've got right here. So the next phase of our work is to try and understand the systematics that be causing this deviation of our points from sitting on our spectral fit, which I've talked about a little bit. Some of it has to do with fine tuning the priors that we've given PCAT, like the minimum flux that it's allowed to see in an image. We're also trying to do this improved dust modeling, which I'll talk about more in just a moment. And we're also going to expand our data set. So as soon as we get done looking at RxJ 1347, we're going to move on to the other 22 clusters in our sample. And we think we might be able to expand that sample by another 20 clusters, which would be really exciting. And then also use the HST and Chandra data as well. So some of the other things we can also do with this work, and I'll talk about that too, is we can calibrate X-ray instruments using this. So if Chandra and XMM Newton, for example, measure at temperature, and they both measure different temperatures for the same cluster, which, spoiler alert, they do, we can use the SC estimated temperature as an independent estimate, and that can be used to help calibrate these other two instruments. And then also potentially looking at future observatories that might use this analysis technique or provide us more data on top of Herschel. We're going to also start writing our report up for RxJ and hopefully have that published within the year. And then I'm hoping to graduate in the spring of 2022. I really, really hope. So the first thing that I'm showing in this graph is all about constraining portions of the far infrared side of the spectrum, like was mentioned before. And we're not the first telescopes, the first analysis projects to come up with this problem. Planck was one of the first to have to deal with this issue. And that's because it was one of the first instruments to have full spectral coverage of the SC effect. And it had 7 different bands. So what I'm showing on the left here is the 7 Planck spectral fits to the SC effect. And you can see that they had that same problem we do, where there's this elevated far infrared data point. And they believe that it is due to this, far infrared thermal dust emission component. And then what I'm showing on the right is what this fit looks like if you add the 3 data points from Herschel Spire, which is what you're seeing here, these 3. And that it's much, much easier to constrain what the far infrared contribution is. So part of the reason that Planck had such a hard time with this is because of this. If you look at the bottom image, this is what Planck saw when it looked at a particular cluster. And the top image is what Herschel sees when it sees a particular cluster, which you're very familiar with now. Planck had really, really big beams, which means that it wasn't able to resolve any of the point sources in any significant way. And that makes it very hard to tell what component of this image is actually seeing sub-millimeter point sources or dust or SC. So they had a really, they did amazing work considering what the field of view looks like. So it caused a poor fit to their higher band data, but it also resulted in an overestimation of the thermal SC effect in a lot of cases because you can't subtract out the components from these other sources. So Herschel, having both the smaller beams and the higher frequency data points, particularly the data point where the SC effect goes to 0, it provides a really strong lever arm to constrain what this thermal dust contamination looks like. In fact, that's really key because if you know that in this reddest band, your SC effect contribution is supposed to be 0, and you think you've modeled everything else correctly, then any elevation in that signal should be due to that thermal dust emission. So that's why we're trying to figure out how to model that really well. And I'll just skip right to the punchline for that, which is for the Goods North field, we definitely looked at what the small Magellanic Cloud would look like using Spire at 250 microns. And inside of PCAT, we've implemented a 2D truncated Fourier series analysis technique where it does a really good job of fitting diffuse structured emission, but also leaving the point sources alone. So what you can see here really quickly is just that we've taken the small Magellanic Cloud as our test case, and we've said, okay, take everything we already told you how to do, but add this Fourier component separation method where you're fitting this diffuse background. And so what you see in this third image is that it's effectively removed that background dust component and left the point sources, and then subtracted the point sources off to give us our median residual again. So we're still actively working on this. It's not completely perfect yet. We want to get a little more precise, and we have to be very careful that this method isn't unduly biasing our SC amplitude in any way, because that would be bad. but these initial results look really promising and we're very excited. I already talked a little bit about the X-ray telescope. I know I'm running out of time, so I'll try to finish. So basically all I'm showing on this left graph is that Chandra on the x-axis and XMM Newton on the y-axis measure different temperatures for every cluster. And that's just because of a calibration difference between the two. And so what I'm showing on the right-hand side is just that you can use the RSC effect, and this is our actual study prediction of what the error bars should look like for our amplitude fits, to sort of compare it against the X-ray temperatures. And you can use that to calibrate Chandra and XMM Newton, which might be a cool side effect of this project. And lastly, speeding right along, Herschel's no longer in operation, and we're hankering for some new data like any good scientist. So the Origin Space Telescope is a proposed mission that I'm really excited about, not only because it's going to be pushing its far infrared sensitivity down 1,000 times what Herschel Spire had, but also because it has more spectral coverage in the far infrared. And so this would be really, really crucial to constraining what the far infrared thermal dust emission looks like in these clusters. And it will be very sensitive to that. So with that, I will stop. Thank you so much for sitting through that. And please let me know if you have any more questions. I'd be happy to sit and chat for it for a while.
All right. Yeah, thank you very much, Victoria, for that wild ride. If anyone here has any questions to ask Victoria, then feel free to speak up.
Hi.
Hi there.
Great talk. So I'm curious how you went from the sort of diffuse residual blob to the SED measurements. What are you assuming as far as spatial structure, temperature structure, or whatever? How does that process work?
Yeah, so you're talking about the spatial blob for the SC effect, right?
Right.
Right, okay. Yeah, we just have a lot of blobs in our data, so I wanted to make sure. So by giving it a template from Bullicam that sort of tells PCAT what the expected spatial extent is, PCAT just treats that as sort of like whatever value it sees in the center of that extended emission is sort of the peak amplitude for the SC effect. And so it's really doing a fit very similar to what it does to identify the point sources in the image. And so that central peak value in the middle of that SC blob is what it's fitting in the amplitude for. It's pretty much just that. It's just that PCAT's determining what that maximum flux level is and then giving that to us. And then we fit the spectrum to it. So I know that other people do this a little bit differently, where they can make like a grid of what they think the Y and temperature should be within a given blob and try to do it pixel by pixel. But we're just doing rather an amplitude fit.
So it's kind of a fixed spatial template that you fit at each wavelength?
Yeah, I would say that's pretty much true, yeah. Yeah, because we kind of tell PCAT what to sort of expect in each of the bands, and so it can fit independently the amplitude in each of them. And then we'll take that number and fit a spectrum. Can you comment on the expected contributions from CCAT Prime? So CCAT Prime is another really cool up and coming instrument. I know that they're going to be covering basically the same band space as Planck did, and then doing it from the ground with higher sensitivities is even more impressive. So I think overall its contribution is going to be pretty significant to just general SC research, right? Like measuring the thermal SC spectrum. It's going to be done in much, much higher resolution, which is going to be fantastic because it just makes all of these problems of separating out the components in your image much, much easier. As far as measuring the relativistic SC, we think it'll still provide significant information for us, but at the same time, it's it's not going to be directed solely towards that portion of the spectrum. And so looking at individual clusters, I don't think is a big part of its mission. From my understanding is that it's going to be doing surveys of the SC effect, which is much more like what Planck did. So it's more going to be geared towards, I'm going to make large stacked catalogs of the SC effect from multiple clusters. And what we're really trying to do is saying, what's the unique thermal properties of this one cluster we're looking at? So it's going to be very cool as like an update to the Planck data set, but it's not going to impact our individual understanding of clusters as much as I think something like origins will.
But sooner. Thanks.
Thank you.
Okay, I think we have time for one or two more questions if anyone else has something they would want to ask.
Sure, I can ask something. So good talk. I was wondering how apples to apples the RSC versus X-ray temperatures are. I imagine you're comparing mass weighted temperatures.
Yeah, that's a good point. So I assume there's a little bit of a fudge factor that we have to account for, and I'd have to ask my advisor more about what that end process looks like for us because we haven't gotten there yet. But you're right that X-ray derived temperatures are usually mass weighted, and so we're dependent on other things than the X-ray data for sure. I'd have to get back to you on more specifically what that looks like though, because I'm not very familiar with it yet.
Sure.
Thank you though.
Okay, and we can probably squeeze in one more question. And unless somebody wants to jump up, I had a question for you real quick, Victoria. So you had mentioned that your source just happened to be a rather frustrating one that your group picked. Is there any system you're using to try and identify better sources for the future?
So I guess to answer that, we have to tell you why we chose RxJ in the first place. And that's because it had so Max J0717 is in our sample for sure. The reason why we didn't start with it, I think, is because, so it is one of the most massive clusters in our sample. It's also one of the hottest. It's, I think, 4 merging subclusters, so it's pretty intense. But I think there were a lot of very bright sources in the center of the image, which were very close to the SC effect. And so the reason we chose RxJ is because it was still fairly hot, but it didn't have any of these central bright radio sources that we would have to contend with along with the SC effect. Wasn't spatially coincident with the SC effect. So that was why we chose RxJ. We didn't account for the fact that it had a high level of cirrus. It's not the worst offender in our sample, but it's definitely not the greatest. It might turn out that Max J0717 doesn't have that much cirrus contamination in the image, which would be kind of funny considering it has a lot of radio source contamination. But yeah, that's kind of, you kind of don't have a lot of control over it, right? Because if you're going to keep most of the clusters in your sample, you just work with what you got. So there's not really any trimming or working around our sample. We just take it and run and see what we can do.
All right, excellent. Well, thank you very much, Victoria, for sharing your research with us today. I just want to point out that next week we have Sarah Nickerson giving a talk. And for those of you still around, I suggest tuning in to the Perseverance live streams, either through the Green Bank Observatory on their Facebook page or through the official NASA live stream, which can be seen many different places, including their YouTube and Twitter accounts. So thank you everyone for attending today's talk, and I hope you all have a good rest of your week.